All right, welcome to APL for advanced users. No, not at all. So this is, since I only have 2 hours, this is a workshop that's going to be pretty condensed. It's going to be a lot of magic tricks, and then we're going to try to unpack it for you guys. But how many of you were here at last year's workshop on APL? 2. Okay, how many of you were at the winter retreat? 2. Okay, so how many of you are complete newbies? All right, and how many of those newbies read the requirements and did them? Of course, no problem. I knew this was going to happen. Never once. Doesn't matter. I've never had anybody do the prerequisites in any workshop I've ever attended, ever. So we'll go with that. That means, how many of you have Dialog already installed on your computer? Okay, you guys are going to be our, so any of you that do, you'll be anchor points. So most of you will be able to work off of a web-based REPL for your APL to try things out. But some of that could be, what's the word? Typing intensive. And so I'm going to be sharing or trying to share a workspace that has all the data. And so those of you who already have Dialog will be able to grab that and use that. So you might want to work together depending on what's convenient and how far we get along on that. Also, the web-based system, if we're all attacking it at the same time and our little IT guy has not been paying attention to his web server stuff, we might crash the thing and then I'll have to go call somebody and get really mad at Jason. But otherwise, we should get started. I'm Aaron Sue, if you don't know. The idea here is I'm going to be showing you a little bit about my research and about this question of how do we do high performance tree manipulation that's parallel, designed from the beginning, from the ground up to run on the GPU. Our goals are things like data parallel by construction, right? It should be maintainable, it should be easy flow, things like that. But GPUs are hard to work with, you know, all of that kind of stuff. Nobody wants to write GPU programming in CUDA. Nobody really wants to write it in OpenCL. They really don't want to write it in something like Accelerate or other Python libraries either, because no matter what you pick, they're actually pretty bad. It's very annoying. And it's difficult to reason about your GPU programs because people haven't been taught those models. Fortunately, APL provides a salve for all of that. And I've been living in this world for a while now, and my research is in a compiler that is itself data parallel by construction, designed to self-host itself on the GPU. So if you unpack all of that, that means that basically you've got a compiler that can compile other code that's running itself on the GPU. And I'm hoping by the time my dissertation is out, it'll fit on one side of a t-shirt. So now, any questions before we get started with anything? Any backgrounds, things, or anything like that? And I don't mind lots and lots and lots of questions, so don't worry about that. You're going to need to be as engaged as possible here. So, nope. OK, so then normally I'm a lot more interactive than this. But since we only have a limited amount of time, I'm going to show you what you guys are going to do, or what we hope that we can play with. And then we're going to go and we're going to deconstruct it, unpack it, and see what we want to do after that, if that makes sense. So to begin with, let's start with trees. So the first thing I want to do is I'm going to start with the tree that I have. So I have a compiler called CodeDefense. It's in the namespace. I have this parser. So we're going to parse a sample program. And actually, we should show you what this program does to start with, right? So this is just a classic little program. And it's a good first starter into your APL world. So those who have seen my workshop before should know what this does.
It was a year ago.
Make a guess. Guess now?
Prime.
Yes. So that's the quadratic primes algorithm. And we're also going to have, well, yeah, so now what we're going to do is we're going to make this a function over an input, and we're going to abstract it a little bit, which I always say never to do, but we're going to do it for the sake of this. Put in a statement separator, apply g to omega. G to x, sorry. Like that, and then run that. So that gives us our primes, right? So this is we're going to basically try to work off of this AST for the moment, because that'll be a pretty straightforward AST. So in the parser that I have, we're going to get our AST, which we will then parse, and we work with whole namespaces. So we're going to put that in there. And assuming I don't break anything, the parser will run and we'll get an AST out of it. So our AST has 3 elements in it. And what I can do is, let's take, the 3 elements are the tree itself, the exports, and the symbols. And so our symbols looks like this. Those are all of the symbols that appeared in the AST. The exports are one single function called f. And the tree looks like this. So this is how I natively think about the trees. After I'm done, I'm hoping to convince you guys that this is actually a good way to work with it. But what we can do is I can say the first thing we need to do is I need to convert this first one. This is what's called a depth vector. This contains all of the edge information in the tree. And I need to convert that into a parent vector, so a pointer representation instead of a depth vector representation. And don't worry if you're not fully understanding what all these concepts are. I'm just trying to sort of show you what we're going to go through. So the first thing that we're going to do with that, actually we're going to dtkn. That's the fields for every node in the AST. Every node in the AST has a depth, a type, a kind, and a name. So we'll extract those out. And then we're going to need a P and an L. And these are our parent and left sibling pointer vectors. So they are going to together replace our depth vector when we use it. So we're going to take that and we're going to group all of our nodes based on their depth. Okay? And now see, the problem is, the reason I'm doing it this way is I encountered a bug in the recent patches to this dialog that causes this to hard crash. Very, very upset with a dialog at this. So I'm hoping to get a DSS patch update very soon for that, but they haven't sent it to me. I told them to get it to me in time for the conference, but of course not. And so we're going to do a 2n-wise reduction, there we go, over that x, if that makes sense. Of course it doesn't. So then we're going to figure out how to update our various, we're going to populate P and L. So we've already populated them under the assumption that they point to themselves, which means every node is a root node floating in this forest. So now we're going to start linking them all up together. The neg1 plus, yeah, okay. So the neg1 plus the I gets the 0 catenate on the 2 equals first axis reduction of I. And so that will link up, basically what that does is that connects all of our siblings together. So every sibling now gets connected and points to its left sibling in the tree. And now we'll take that and we need to update the parent vector. So the parent vector, we simply take our incoming set of groups and do the interval index lookup on those. And yeah, good. And I don't care about the result, so I'm going to discard that. And oh, what did I do? I used what did I do? Did I not do the assignment? What did I use? Oh, whoops. Yeah, forgot to convert that to a index. Okay, so now we have P and L vectors that represent the tree in the same way that our depth vector did. So this is the first part of my compiler. So you can see that first line up there. Second line, actually. So now what we can do is we can actually print this tree. So let's pretty print the tree. And we'll need, let's draw the tree horizontally. And that's what that tree looks like. And of course, if we want, we can draw it vertically as well. And if we want to even more, pass the AST into this, get tree, and pass PL on the other side, and we can generate the labels. And so let's look at the parent vector, the parent vector, the left sibling, and the let's do that. And let's pass in PLTKN and pass in our exports and our symbols on this side. And then let's do PL omega concatenated with iota of the cons of the first omega, alpha, and use the vertical horizontal drawing of the two-take of omega. Yes, okay. So now we've rendered the tree seeing our individual fields. And to more clearly see this, I can take this and instead just run with the IDs first. So that's what every ID in the tree looks like. So this is the unique identifier for every node in the tree. Or I can take the parent vector, and so you can see which parent it belongs to. And I can combine these two together and show both the parent vector and its ID. Let's put the ID first. All right, so this is 23, 24. This is a child of 23, and so forth, right? And if instead of the parent vector, I use the left vector, you can see how the siblings relate to each other here. So the left sibling of 20 is 18, 20, and so forth down the line. Okay, so now what's the first step in doing our compiler? Well, the first problem, yes?
Could you just connect that back to the original arrays you had?
These? Yeah.
Yeah, or even those four you started with. Like, you've got the result of, like, can you just identify sort of what these...
Oh, the original depth vector? Yeah, we can use the depth vector in here. So if I include the depth vector in this computation, and I put the depth vector in, so that's the depth vector of the tree. Is that what you were asking for?
Yeah, just walking through it with your finger on the numbers.
Yeah, so root node has a depth of 0. Our enclosing function f has a depth of 1, or the binding node that holds f. Then we get to the function 2, and then it has 2 children, the function definition and the expression, which are all at depth 3 and so on down the line. I'm going fast here because I just want you to see the code, and then you guys are going to unpack it later on. We're going to go through all of this in detail, right? So I just want you to get a picture of where we're headed, right? So then let's speed it up. So you've got kind of a flavor here, right? So let's speed this up a bit, and let's run the first compiler pass, which is these 2 lines, these 3 lines here. Right? And hopefully I don't break anything. So let's get a good version that I want to print. Let's print the whole thing. It's really helpful if we can see the whole thing. So I actually want to do, I'm not going to do the parent vector anymore or the left sibling, but I'm going to include some other data in there. I'm not going to include the ID. Yeah, so this will include the data as well. So here you can see the tree. We have a binding node to f. This is a function that has a binding node to g, which is a function that has an expression which applies 2 equals to plus reduction of, and so forth down the line. So now what I want to do is first, I don't like having that module node there. So I convert the module node to a function node and insert an export function at the end. So in other words, this top level function is the exporter function, which will then export all the top level functions in the module to our API, our external interface. And then we don't like nested functions in a compiler, so we'll run that. And this will lift all of the functions up. So now all of our functions are at the top level, and where they were originally, you can see up there, that binding node to G has been replaced with a variable that refers to the function by its ID, 4 in this case. And here the variable is 2 for that other function. So we've done our function lifting. So that's another few lines. And the next one is expression flattening. I'm not happy with this pass yet. So I was playing with it last night to see if I could figure out how I best wanted to demo it for you. But I'll try to show you what is there so far, just so you can, oh, yeah, see, I was playing with it. So anyways, let's leave it at that, because that's enough for you guys to unpack right now, right? So we've done 2 compiler passes. One is just inserting a couple of nodes down here, and one is, and the other is lifting up functions, manipulating the tree into the top level. And then as an extra bonus, if you guys are feeling comfortable with that, we'll arbitrarily delete a node from the AST next. So, all right. There's some code. You saw some stuff that we did. So let's unpack it, shall we? Yay? Let's start with a total reset. So I'm going to do here, and I think we want to end here. So PLTKN. So then we're going to do PLTKN gets codefense TT of the AST. All right, so that's what our AST comes out as after we've done our flattening. And great. OK, so we can go from point A to point B now. All right, so now you guys can only try APL.org as your starting point. But you guys should all either get to try-APL or get to your dialog terminals. And let's start going through this slowly, individually. And let's focus on whatever part you guys are most confused about first, and then go from there. All right? So, yeah. Any questions now? Well, now you have to have questions. There's no getting out of it. I have arranged it so that there must be questions. So, where shall we start?
I would just like to understand the tree encoding better.
Okay.
I mean,
Yeah.
You've explained sort of the depth vector, but everything between that and the diagram appearing is not very clear.
I didn't show you guys the tree drawing functions. I should have done that. Not that it's going to help at all, but whoops, I need to close. Oh, no. I want the other one. Yeah, let's close that. Make it big. It's big, yay! Okay, so this is what draws the tree in vertical and horizontal. So you've got our pretty print the tree, label the tree, and then draw vertical, draw horizontal, and some helpers for those drawing functions. And we can cover this in detail as well. But let's look at DPL, and let's start at the let's start here. So PL and D, if we look at those, all right. So this is the bread and butter of the stuff. The other stuff are just fields that point to that are fields for the nodes. These contains the edge information and all the extra information. So when we start, the depth vector is an ordered vector that contains the depth of the nodes, and the order is in a depth first pre-order traversal of the tree. So that's how we represent that. Now the problem with that is to do this stuff efficiently in parallel, walking that tree can be done. So I've shown how to do it in previous research. The problem is that the computational complexity is a little higher than you might like, and the memory costs can be higher because you have to have some way of identifying your parent and getting the parent-child relationships between the nodes, and that's very important. So for example, knowing that this parent is here or here, now there's an ordering dependence. So how do you do that? You have to walk it or do whatever. And so walking it means that you potentially have to walk, if you were going to walk backwards, you might potentially have to walk linearly in the size of the tree. So there's a trick you can play using what's called path matrices to compute these using path vectors that you can compare, things like that. You can do this in parallel, but there's an issue with traversal, basically. So if we convert this to say instead, we have a pair of unordered vectors. The ordering does not matter. And the parent vector contains a pointer to the node's parent, and the left sibling contains a pointer to the left sibling of that node. That encodes all of the information in the depth vector, just without an ordering dependency. And so now the dependency is only a lookup cost. So to extract all of the same information, the total complexity is the computational critical path is basically the depth of the tree, which can be a constant factor in human written code because people don't write heavily nested functions, or they limit themselves. There's a hard limit in their style guides to how deep their nesting can go. And in that case, the critical path is essentially 1. A large 1, but it's still a 1, or a big O1. And then generally, we're aiming for a computational complexity of n log n. Cubic or quadratic is sometimes acceptable, and so forth. But we aim for a critical path of log n or better.
You're able to parallelize over all the GPU
Yes.
Completely, right?
Yeah.
So
Yeah, over every node, yeah. So does this make sense as far as the encoding goes? All right, so the question is, how do we then use this, right? So, or I mean, I guess that would be the next question. Or I'm not sure exactly what you want to see in the encoding, so we should unpack that.
Just trying to wrap my head at what trivial examples would look like and how to generalize it.
Yeah, so we can parse a slightly less complicated tree, for instance. If we make our AST the average function, which I think will work. Keep in mind you're literally running on the bleeding edge of what I'm playing with on the compiler right now here. So, so if instead the average is the sum of the inputs divided by the tally. So in other words, the count, the sum divided by the count, right? So now that AST, we can say DTKN. We can get the trees for that. And we can get the initial fields from the tree. And then we can do a do this. Let's do our conversion. And so now we have a P and an L. These are shorter, right? So our D, P, and L, before we do any additional processing, looks like this. So if we want to line those numbers up, we need to catenate them. So we can catenate along the first axis along here, and then do a catenation here, and it looks like that. So here's our depth vector, here's the parent, equivalent parent, and left sibling node. And I guess to help out with that a little bit more, we can tack on the actual node ID at the top. And if we want to be funny, yeah, let's be funny. Let's see. Because I don't like that much. There we go. Okay.
There's 14 nodes in the AST just for the average function.
Yeah. So if we were to print this function, this guy out, let's go.
There's a max that says to.
Oh. Where's my printer? I want it to print. I want the pretty tree. Yeah, that guy. Oh, I see what I did. Yeah, all right. Let's pretty print that version. Yeah, all right. So if we want that version there, will that give me what I want? Probably. Yeah, that'll do, right? So now you can compare what the data is and how that data looks visually.
Could you just bring up the original expression underneath it?
Yeah. So the original expression is a namespace. Actually, let's call that source, our original source. The average function, which is the first axis sum of omega divided by the tally of omega.
Okay. So what are the CV1 average? What is the individual column?
So those are the nodes. So we have a top level module. Then we have a binding node, which says somebody bound something. It's a function class, which is 1. 0 is for data.
There we go.
The name is, this is the type and the kind, the T and the K fields. So we have the type, which is the broad class, and subkinds for finer grained resolution of information related to those nodes. It's called the average function, and the value which is bound to average is a function node. It's a standard function, which is class 1, and a kind 1, sorry. And it has one expression in it. And that expression is a dyadic expression, meaning it has 2 arguments. Its first or left argument is a monadic expression, which contains one argument applied to a function. That function is a derived function from an operator that was applied, that operator being first axis reduction, given plus. So this is a higher order function. Derived function, then applied to omega to get the count, which we then divide by this expression, which is the count of omega.
I see. So the top's like the left-hand side, the bottom's the right-hand side.
Yeah, so we don't have to visualize it like this. We can, since this is small enough, we can draw this vertically. And that's how the AST looks. Yes?
So, yeah, I just want to sort of say in my words what I think your tree data structure.
Absolutely. So lecture is completely over now. We should be, you could play, you can type this stuff into try APL, try to mimic what's happening here, anything like that. Yeah.
Right. So,
absolutely.
Yeah, I'm not familiar with APL particularly. I've looked at it a couple times. But
Right, right.
So like a standard tree data structure to me would be, like the stock standard would be you have two child pointers, a left and a right, maybe you want more, like in a different language.
Yeah. So let's do that representation.
Well, let me just
Okay.
finish up what I think what
Okay.
you have there
Sure.
is. So instead, what you want to do is, because it's like APL is all about like multi-dimensional arrays. You want like everything to be in terms of multi-dimensional arrays. Is that fair?
Everything's an array.
Yeah. Okay. So instead of doing like that pointerized structure, you built a table where you're indexing which node you're talking about by the index in the table.
So there's a view you can apply to this to say this is just a relational database table. There's a way you can look at that. Yeah. In fact, this encoding in the APL community is known as an inverse tableized form of
Okay, so
a matrix.
Is a standardized data structure.
The parent vector is a standard data structure in high performance computing. The inverted table structure is a standard structure used in the APL community. And yeah. The matrix is a standard data structure everywhere but in FP.
Yeah, so you have one number that's the depth you're down in the tree that you're storing.
Yep. Now keep in mind we're ignoring that now, more or less.
Okay, but
That's your source of truth.
That's the source that came in from the parser because it's easier to build the tree using that.
And you have one number that's the parent, so the index of where you, if you want to.
Now try not to think of these as numbers. When you see that, that's a pointer. We're manipulating pointers here.
Right.
Yeah.
Okay.
Yeah.
And then the other number you have is just your left sibling.
Yeah.
Okay. Okay.
So there could be an invisible dashed line going.
Right. So
Yeah.
then it seemed, in this format, it seems a not straightforward operation to just traverse down the tree because you don't have a direct link.
Yes. Yes. Yes.
And-
I'm glad I didn't have to tell anybody that. Yes. All right. Yeah.
Okay, so what operations does this structure make easy?
Exactly. Yes.
And inversely, which one does it make hard?
Yeah.
You can go from the leaf to up and parallelize operation with the leaf.
Exactly. So traditional compiler design or traditional tree manipulation design is always designed around structural recursion from the root node. That's how you do trees. In fact, I have struggled to find anything after the 1960s that does anything different. And you know, this like my related work section related to this tiny. Everybody has standardized on one single way to do trees traversals, or one single way to do tree manipulations. Traversals get a different approach, but if you actually start wanting to change the structure of the tree, structural recursion in a recursive descent style is how you do it. That is how they always do it. Whether you're in OOP, functional programming, C, Haskell, everybody does it that way. So the benefit of doing it top down is that you can leverage the stack, because the stack now encodes all of the path information, all of the edge information in your tree in a localized form that you can then handle for each node individually. So it's a very local view way of looking at it. And you can go down and propagate that information naturally using your programming language control flow to manage the path in the tree. So that's a very natural way to do it in something like Haskell, because Haskell has a lot of facilities for that style of recursion, right? The problem with going top down in that fashion is that it's almost impossible to practically parallelize on a GPU. And the reason is that you have to propagate too much data, and it's the overheads for working with those data structures are way, way, way too high. The way people parallelize that stuff, they don't, right? Every compiler project that's tried to parallelize their stuff has decided that it's not worth it. Instead, they do coarse-grained parallelism, and they say, we'll just call multiple compilers on multiple modules, right? The reason being that there's so much synchronization overhead with communicating up and down the call stack that you have to handle that synchronization somehow. And generally, the only thing that can manage that at this point is a work-stealing scheduler. Because when you go down the tree, you don't know a priori how wide the tree is or how deep the tree is in terms of information. And so if you can't predict how much parallelism you're going to have to spawn your parallelism dynamically, right? And so when you chase pointers downwards, it makes it easy to think about the paths, but it makes it very, very difficult to think SIMD or think in parallel in a way that has low overheads. And it's difficult to find things in that fashion. So instead, we almost universally in this structure favor a bottom up, as you were saying. You start at the leaves, and the way it works is you start by saying, hey, we're just going to assume max parallelism. Every single node gets its own thread. And we use very, very small instructions that are lightweight on each of those. So the SIMD operations then flow upwards, and you get a different pattern. So I actually have a diagram of this.
So that's why you only have your left sibling and your parents.
Right.
Okay.
Let's see. Yeah, all right. So this is the traditional descent, right? Start at the top, go down, and parallelism begins to increase dynamically. And you can't know ahead of time how it works. Our structure is instead this. So we start with, if our tree has this structure, we start with all the nodes being parallel. We go up, we maintain that same parallelism across the board, and we propagate small bits of data across rather than large data structures across. And so we don't have as much data duplication problems, and we don't have the issues of how to keep parallelism around because our tree just sort of spreads out along the leaves. Yes?
Sorry, so how do you maintain the 8 wide parallelism as you go up the tree?
Yeah, so let's look at that. So let's look at how we do the basic tree walking. So with this guy here, it's not going to be very yeah, we can do this. So let's ask a question, right? One of the common questions we ask is, what is the nearest ancestor that has a certain node type? So for function lifting, for instance, if you're going to lift up functions, you need to know what is the nearest enclosing function, or what is the enclosing scope that I'm in for something like this, or for variable lookup. For expression flattening, you need to know what is the top level root expression that I'm engaged in, or something like this. So the simplest way is you can ask, in this we have our parent vector, and we can say the type of all the nodes is T. The type of all the parents is this. So now what we can do is we can do, let's make sure our index function is defined. Yeah. So we can start with a parent vector and ask at every step, let's say, are you an expression yet, right? So make sure I have all this here. Yeah. All right. So we can say, is your type, if your type is not equal to 2, keep going. And we start with the initial parent vector, right? And so what we've done now is, in parallel in SIMD, we've identified the nearest expression node that encloses any given node. Yes?
So, I mean, traditionally, no compiler expert, but normally you take a top-down approach because
Right.
you have to compile your dependencies before you can compile your
Because you're trying to manage, because a lot of information is at the top of the tree that you're trying to propagate down.
Yeah, so
Yeah.
are you basically duping, now that you're taking a bottom-up approach, are you basically duping the stuff at the top so that you're compiling it multiple times, or is that?
No, we don't compile it multiple times. We fragment the data into very fine-grained levels and dupe it along each single thread. So for instance, to do this computation, we start with the parent vector. And every single time we go up, we get a new vector of the same size. It just has different information in it.
Okay.
Right, so the first, let's print the iterations out, actually.
Yeah. and Are you basically doing max traversal for the depth, or does it stop?
So it depends on where the information is. On a traversal like this, the critical path is the depth of the tree. Yeah.
But I don't understand the expression as it's written. So can you clarify whether what is that conditional, or is it just blindly recursing the maximum number of depths?
No.
Got it.
This is the fixed point function. So it runs until it no longer needs to run to get its data. Whoops, let's see. Yeah, okay. So the way to read this is it started and it found these nodes that weren't pointing at whose parents were not expression nodes, right? And then it found these nodes whose parents weren't expression nodes. And then it found these, and then it was done. And then it found the parent nodes for everything.
Wait, so 0 the node ID, or is that the?
0 are the nodes, are not the nodes, the parents of a given node. So we started with, let's print out the parent vector instead of the actual found nodes. So let's go here. We'll wrap this guy up. Apply this guy here. Close that off like that, and go like that with. So every iteration, we're seeing this parent vector get updated until we stabilize. Now you notice we didn't have to go all the way up the tree to do this. That's because we were looking for nodes that were very close by, so very few iterations had to be run.
And just how does it do the conversions check?
Conversions check?
How does it know that the last two are equal? Was it literally, compare
This
everything?
is the equivalence operation.
No, I know.
Yeah.
How does that get implemented?
That's up to the implementer. There are multiple ways to do it.
Right, and you're writing a compiler. So
Yes.
What did you choose?
There are two different ways to do it, depending on the type of data you're dealing with. If you're dealing with very, very large data, where you're memory bound and incurring a little computational overhead isn't going to be a problem, then you can maintain basically an index set into P that you're still working on, and that shrinks over time until it gets to 0. The other one is you can just do all equals across the board in parallel on them and just terminate each thread when it's done. The difference is one might have more branch divergence than the other. One is much simpler computationally than the other, so it depends on where your performance limitations are in terms of how you want to apply it. So for small utility things where I don't expect it to run very hard or churn very hard, and it's more important that I get a fast result over a relatively fixed size and everything's going to be pretty balanced, I generally just use the this mechanism where you just do it all in parallel, do every thread in parallel all the time up until it's fixed. So every iteration will have n number of comparisons in parallel. But then the more complicated ones, like larger, bigger data that is very unbalanced, then I'll do the other method.
So the numbers are the pointers to the parent in some index.
Yes. So for each node, so this is a column for node 0,
Yes.
column for node 1, etc. For each node, we're looking at that node's parent.
And that's pointing to some other array.
Yeah. And so this is our basic tree walk up. Yes.
And when you said you had these two implementation strategies, your runtime chooses between the two depending on the size of vector?
The runtime can make that choice. The runtime will probably be the one that needs to make the choice. Or you can just write out the other way, and one way or the other, and force the the implementer to do it your way if you want. It's a little more verbose, but yeah. This form that I've written here gives the compiler the most flexibility in terms of what it wants to do. But you can force it. Really, the main thing is you only want to force it when you want to use that shrinking index set method. And when that's the case, you can explicitly write the code that way, and it will run that way. Yes.
This is executing on on threads in a warp, let's say, on in a GPU.
Yes.
Right? And then if one thread finishes, do you essentially mask off in the implementation?
What will happen in CUDA, there are different ways of implementing this. One is kernel, 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 each size. That's a reduction index set, or running that way. The other way is giving each of these a thread, so it's a little while loop in each thread. And then they will, once the warp is fully complete and they're all idle, that warp will die and the next one will get brought in and so forth along the lines. Now, it gives an interesting optimization. So it can be very difficult to have readable code that's also optimized. Well, one of the things we can do here is, because P is unordered, we can arbitrarily permute P for data locality based on the type of traversal access patterns we want to do. And we can do that any time we want through the tree in order to maximize our locality for that specific problem. And it costs almost nothing. It's very, very cheap. And it costs almost nothing in terms of user code. The code to do something like that is smaller than this line of code. You can actually see that in B here. So in here, one of the first things I do is I use the left sibling to reorder all the nodes so that all the left siblings appear in an ordered fashion in the tree. And I do that up here, where I start with an ordering vector that's all zeros, then compute an ordering vector off of L, sort that ordering vector, and then just reorder things. And we're good to go. And so all my computations are based off of that indexing set. And so I can use this for optimization. I can use this for anything, because now I can say, oh, well, that access pattern is really complex. It's adding complexity to my code. I'll just reorder it so I can assume that the thing I need to deal with is just one index less than mine, to my left or to my right, or something like this. And you can do this arbitrarily. You're not restricted to a specific type of access pattern. You can choose how you want to do that. So one of the things that you might do, for instance, if you're chasing pointers up, you want to keep siblings close together because they'll have common parents, which will then lead to warps dying faster and give you more free up space faster. Or if you know that you're going to be accessing certain classes, for example, we access all the expressions or all the variables, you can sort based on the type so that when you access the patterns, all of the things that you're accessing are right next to each other in the memory. And you can do this at a high level rather than at a low level. And you don't have to manage this inside of CUDA's shared memory architecture or something like this.
When you mention things stabilize, what does that mean? You basically fully evaluate
The function runs to a fixed point.
Okay.
Yeah. You guys should try it. Try the code. Sorry? No, base 64 only uses ASCII. I use full UTF-8.
Can we download that workspace?
Yeah, so let me do a...
The working version of it.
Well, I'm going to just go ahead and do the fast and wild version. All right, so now if you go to the codefunds repository, that workspace will be in there, and all the data that we've... well, let me save this. There you go. And do another commit. Okay. All right, so if you grab that workspace, it will have the data structures we were just playing with. And you can use try APL, and you can just type in the small data structures. So if we look at our PLTKND, you can just type these in and work directly off of these. And if there's a git paste, no, you can copy the drawing functions out of the GitHub workspace, yeah.
I think I just think, where do I find your...
Just search code -e funds.
Yeah.
Which file is it?
codefunds.dws will be the workspace.
Okay.
The drawing functions, if you're using try APL and you want to copy in some drawing functions, that's in b.cd. And you want, I'm surprised nobody commented on pp3. I'm very proud of that naming convention. For pretty print the tree.
What was the 3? Because
Yeah.
it makes a tree sound.
Yeah. Because I'm Asian. Pretty
You're
tree.
teaching Latin with the Chinese with their writing system, and it was bad when they did it.
What?
How a lot of the Chinese symbols are basically based on rhymes.
Oh yeah.
Like little visual puns.
I like
Yeah,
that.
yeah. That's the way it goes. This is great.
Yes. Maybe a different question, but
Yeah.
What journals publish papers with APL?
The Vector APL journal is probably the main one that's hardcore dedicated to APL.
And that's
Yeah, you can still submit articles to that and do stuff. It's more of like a workshop class type thing. It's or user meeting type thing. It's not what I would call a top tier journal at all. It's just it's the old school sense of a journal. But yeah, Vector from the British APL Association. I think that's vector.org.uk. Yes.
The question in between the screen switching.
Yes.
You seem to have some notes that were typed out that were explaining some of this. Is this
Oh, that's part of my dissertation.
okay?
Yeah.
Is that published yet?
It's available on LeanPub as a pre-alpha. It's got like 20 or 30 pages in it. and it's probably going to have something like 400 pages. But just try to kill me here. Okay, yeah, it will probably have, like 300 or 400 pages in it. Right now it's like at 12% or something like that. And it's subject to massive amounts of change all the friggin' time. So, however, if any of you wants that, I can get you access. I can send you the link to that, and you can read it and provide comments and work on it and things like that. Yeah.
I'd definitely be interested.
But I also have all of my others. If you go to my blog and look at Getting Started with APL, that has all my other stuff. Yeah. But yeah, so this is the time for you guys to figure all this stuff out. This is where you need to ask questions, try to run this stuff on your computers, play with it, see what breaks. And if you guys think you've got this basic tree walk down, then we can start exploring some of the other stuff. Or we can explore some of the other stuff now.
Maybe I missed it. How do we open up do we need the dialogue?
If you're going to access the workspace, you need Dialog APL. If you don't have it, you can just copy these pieces of data into your web session and just copy them in. You would just do something like P, for instance, gets 0, 0, 1, 2, 3, 4, 5, 5, 4, 8, 3, 3, 11, 11, 13. Yeah, it'll take like 15 seconds or 30 seconds to input the data.
How do you load in the...
So you can double click. Oh wait, are you on a Mac? Of course you are. You open up Dialog from the Applications folder, and then you go to File, Open or something, or Load or something like that, and then you load that file in.
So I don't have the file loaded?
Oh no. What version of What version of Dialog do you have? I'm hoping.
16.
Oh, good, good. So what the?
Connect.
Oh, where are you? Oh wait, you're in here. Yeah. You're here. So we go here. Yeah.
You have to actually...
Oh, you have to press it. Really? Really, Dialog? Really? You're gonna do that to us? Okay. I think.
Do you have to do something squirrely like drag an icon?
No, it never. Whoa.
Oh, that's pretty cool.
What just happened?
I have it in full screen.
Oh.
Yeah.
Okay, so since that. What the? Whoa! It's a Mac! Save me, somebody!
last year we just downloaded, but he had a link.
Oh, wow. Okay, so you've got another session here. All right, so you can type in the path. You can just say load, and, yeah, and then type the full path.
Full path.
Yeah.